we'll get set up here. And then we'll get going. One minute and I'll give an intro and then we'll get started. All right, let's go. This is made up of wires, and we are decompiling Castlevania Symphony of the Night. Castlevania Symphony of the Night was a game originally released for the PlayStation 1. It released, I believe, in 1995. I missed it in 95. I did have a PlayStation, original PlayStation. I probably saw Castlevania. I saw that it was a 2D game when the hotness was all 3D games, and dismissed it. And it was about 20 years until I finally played it after hearing that it was possibly the greatest game of all time. When my kids were little and I had to rock them at night, I would play Symphony of the Night, and I loved it, and it is one of the greatest games of all time. The Castlevania Symphony of the Night decompilation project is attempting to take all the various versions of Symphony of the Night, the original PlayStation version, the PSP version, the Xbox version, other variants that have been released along the way, decompiling them to get back to original source code, and then being able to compile that source code back to the exact binaries that were created for each version of the game. And hopefully, once that source code is available, being able to make mods, make other versions of the game. So the last couple weeks we have been decompiling various functions throughout the weapon module, the weapon 0 module. If you're not familiar with the project, there is about 10 or so modules that have been pulled out, and those are kind of the starting point, primarily focusing on PlayStation 1. There are a few things taken from the PSP version to compare them to the original version, and what has been learned along the way is that the decompiler for the PSP version often has more accurate decompilation, and that we can produce code that compiles both to the PSP and to the PlayStation, producing the correct binary outputs for each of those. It appears that the code from the PlayStation version was taken and recompiled for the PSP. Sometimes the code that we generate for the PlayStation version doesn't compile exactly on the PSP, but the PSP code typically will compile back to exactly what was on the PlayStation. The compiler was a little more advanced for the PSP, and so unused functions were removed, and other optimizations were applied that we don't get on the PlayStation version. So we have actually much more dead code in objects in the PlayStation version that don't always translate to what's on the PSP. If you go to SOTN.z.dev, you can see progress on some of the modules that have been completed. The DRA.bin module is the main game engine. There's one function left there to decompile. Otherwise, it's all been decompiled. The Richter program is complete. We're going to be working on weapon. There are a lot of empty functions within weapons, optional things that most weapons don't implement, and so that's why there's a huge disparity between the amount of code that's covered versus the number of the functions that's covered, and that's slowly working up. We're going to focus there because there's a lot of low-hanging fruit that we can get to. For stages, most of the stages that we've pulled out have been fully decompiled with the exception of the nightmare stage and the stage selection stage. The debug room has some overlap with existing functions that just haven't been mapped yet. The same thing with NO3. I believe NO3, everything that's left in NO3 has been decompiled in other stages, but just hasn't been mapped. And several of the other stages are all at 100%. Stage selection was the other one that's missing one function, and that one's pretty close. And then several more. So, as I said, we're going to be focusing on weapons. There's many small functions there that are good for decompiling in a live stream. Last week, we did a few in Weapon 15. I forget which weapon Weapon 15 is. One of them was Shield Rod. The other, I'm not sure. But we got a full decompilation on the 008 function as well as the 008 from Weapon 7. And these were submitted to GitHub during the stream, and both of those have been accepted and pulled into the repo. There is a Discord. If you go to SOTN.z.dev, you can find the Discord server. Chat there if you're interested. It's always useful to have more people who can decompile. So if you're a programmer and love SOTN and want a side project, more fun for everybody. So one of the main tools that we're going to be using is decomp.me. It is a collaborative editor for decompiling. It'll take some assembly code and allow you to write C code side by side and try to get a match in that compiled C code versus the assembly that you upload. So the way that Symphony of the Night is laid out, there's several objects that are stored on the disk for the PlayStation version. Those objects are read into memory at particular memory addresses. This is called overlays. And each of these overlays has several functions in it, as well as assets, sprite data, sound data, other things like that get loaded. And there's tools like Splat64 that were written for decompiling N64 code that are being reused now to help decompile those objects. So Splat64 takes one of those objects, is able to find logical boundaries in code, so different functions within that code, data sections in that code, and help us figure out which pieces are things that we need to treat as data versus things that need to be treated as code, and what the boundaries are for each of those things. So the Splat64 configuration for each of these objects has been done, the ones that we're going to look at today. So we're just taking what Splat64 has done, which is extracted functions, turn them into assembly files, and we're going to take those assembly files then and convert them into code. And the code that we want to produce needs to compile back exactly to what the object looked like on disk. So let's start by finding a function to decompile, and to that we're going to go to a terminal where the project's set up already. And by default, the Symphony of the Night Decompile project will build the US PlayStation 1 release. For the objects that it has been configured to build, it will check to see if the built product is identical to what was on the disk. And so for these, the way this project is currently set up, I have a few functions that I've decompiled in this branch already, but everything is matching. What we're focusing on primarily is this weapon module, and so we're going to be tweaking it, and probably over the span of this stream, this will be failing at some points, but we'll get it back to OK by the end. One way or another, either by deleting our code or hopefully getting a match. So when these files are extracted, we get C code files with placeholders in them, and those placeholders include some assembly file. So in this case, for weapon 7, which is the shield rod, the entity weapon attack function has not been decompiled yet. So there's a line for including some assembly for entity weapon attack. I don't think we're going to work on that because it's a little too long to complete in about an hour or so during a live stream. But that's how that assembly is brought in. What I like to do is go to the assembly directory and give me 1 second. I go to the assembly directory for weapons, look for non-matching functions. I'm looking for functions that end in a .s because those are assembly files. I'm going to get a listing for those. I want the size, which is going to be in field 7, the name, field 11, and I'm going to sort those by size, of course. I meant awk instead of print. So here's a list of assembly files that haven't been decompiled yet. I typically start with some of the smaller ones because they're easier to do. And so in this case, we're going to look at weapon 22. I don't know what weapon 22 is offhand, but we'll take that one off screen. I'm going to copy the contents of that. We'll open it first and look at those. And we can look at the C file alongside of it. So this is entity weapon attack. So we have on line 9 here, we have where this assembly file is being included, the assembly right next to it, and then most of the rest of this weapon is done. So we might be able to finish this. Yeah, this is the last one. So this is the magic missile. Fun. I'm going to off-screen copy that to paste it into decomp.me. And just skimming through this, it's a relatively straightforward function. There likely is going to be some surprises, but we'll see. That's the fun of decompiling things in front of an audience. You never know what's going to happen. So decomp.me allows you to paste some assembly in. You have the assembly that you're going to be targeting, trying to decompile. You also have a context, which is similar to a header file that might be included. It has declarations that'll be useful for the decompiler to understand structures that might be in place, other function declarations, so it knows the calling convention when setting up, arguments on the stack, and other things like that. For the most part, the context that I have in there, it saves your context from the last time you created one. Should be good with the exception of a few function declarations, and we'll get into that after I decompile. We're decompiling for the PlayStation, and there's already a preset for Symphony of the Night, which selects the PlayStation SDK and the correct version of GCC to generate code that'll match. So I paste it in my assembly. I'm going to create a scratch. And this will give us a best effort decompilation that may or may not actually recompile the first time. It's kind of funny because the decompiler can't always produce code that will recompile. And mostly what we're missing is some of the declarations that weren't in the context, and so the decompiler doesn't know exactly what the signatures for those are. So we're going to find the signatures, and we're going to do that basically by going back to the code, and other people have determined these signatures already. These are going to be in the weapon directory. So destroy entity weapon has that kind of shape. So in the context, we'll add that as a declaration, and we can get rid of it from our source code, and we'll see the warnings should slowly start going away as we get these. Set sprite bank is another one. Now we have a variable that's global. We don't know what it is. We can look to see where it is being used. It's being used in this set sprite bank. I happen to know what this this variable is given a special symbol at build time. We won't worry about that now, but this is going to be a sprite parts array. And okay, and then the last one, let's see, we have conflicting types. I'll talk about that in a second. Line 46, there is something at an offset of hex 50 that wasn't known to the decompiler. This is actually a little strange because this field is known and is mapped. I believe that's animation frame. Anim frame, what's the name? anim curve frame, the current animation frame. I guess the reason the decompiler doesn't know is because for some reason this is being treated as a 32-bit signed integer in some places and a 16-bit signed integer other places, and the way that addressing works, we have this predefined as a 16-bit integer, but this code is treating it as a 32-bit integer. This happens throughout the code base where different parts of structs are treated differently, but not in a typical way where you might have a union in those structs. So we'll try to figure that out along the way. I ran into one of these yesterday as well. It has been solved in other places, but it's not something that I have run into before, or before yesterday, that is. So we still have a few warnings, problems in our project. The first one is conflicting types for string compare, string copy, length, memcopy. These are because the PlayStation SDK defines these functions and expects you to link against them, as opposed to versions that GCC might generate automatically. So we add the no built-in option to GCC. We're going to save. And we still have an issue with line 46, probably related to the size. And then on line 17, there's an issue, and we'll talk about that in a second. So we have a project that's compiling, which is great. We're at 68% match. So if we look at this right side of the browser window, we have two columns. The target column is the assembly that we're trying to reproduce, and the current column is the assembly that the C code that we currently have is producing. And different colors indicate that there's mismatches for various reasons, and so our job now is to go through and try to figure out what the cause of those mismatches is. To start that process, I like to take as many of these declarations out of the code and put them into the context. Some of those we'll need back when copying back into the project, others we won't. When we see player underscore global variable, it's a placeholder for a struct field access that has been given symbol mapping during the decompilation process to make it easier for decompilers, but it's not how the final code needs to work. We need that field access to change how that data is loaded. So we'll go and look at some of those. We can look for player underscore, and we see the Z priority here. We get a highlight where this code is being generated over here, and we're going to change from a direct symbol-based memory access to this struct access, and that changes the order. In this case, we were at 68%. This is actually going to drop our match a little bit, but that's okay because we know that this is correct from other examples in the code. We're going to do the same here, and we can get rid of these declarations then. This G player is similar, so we're going to that's going to be struct access as well, and instead of an offset like that, we're going to have array access into this object. Some of this is really from experience, if you're decompiling this new, it's things that you'll run into, and eventually they'll kind of become second nature. So we can get rid of this variable as well. And then hand ID, that's what hand the current weapon is being used. We need that, but it's defined elsewhere, so we'll copy that into the context as well. So that's just some cleanup to get the context prepared before we start any real work decompiling. The next piece is getting some standard conventions. Most of the time, entity-related functions are treated like class methods that you would do in a modern programming language. So while C++ existed in 1995, it wasn't the powerhouse in games that it currently is. Actually, using C to program games was a pretty novel concept. And so many of the entity-related methods take a first argument, which is an entity that we're going to treat as if it's a this pointer or self in some other languages. So we're going to replace all the arg0, which is something the decompiler just chooses. We're going to change it to self, just to make things easier to read. And that's it for the most part for the project setup. Now we'll start going line by line and both modifying things that as convention are known to be one way or another, and some things we'll refer back to the assembly to see if there's anything that needs to change. One of the things that's very typical, and I think it's based on the way C was written at the time, the GCC compiler that's being used for the PlayStation required variable declarations to come first in a method. And so often in these methods we find there's not a lot of variables that are used. And often there's no additional variables used aside from what's passed in as arguments. And so that's one of our guiding ideas is, when possible, remove variables. There's other places where variables are used where it doesn't make a lot of sense, but the code doesn't compile or it doesn't match without those variables in place. And so we'll kind of see both probably throughout this decompilation. So one of the first things I'm going to do is get rid of this temporary variable for the step. So step is a field in each entity struct which tracks the state machine for each step. So we're just taking that variable, putting it directly into the switch, and it's likely temp v1 is never used again anywhere else. So we can get rid of that as well. That doesn't change. So along the way, I didn't mention this at the beginning, we're trying to get this 3900 number, we're trying to get that down to a 0 or as close to 0 as possible, and we're trying to get the compilation percentage up to 100% or as close as possible. Due to field and struct access, there are some immediate values that won't match exactly, but when we compile them into the final project, they will match. One thing that's a little interesting, and if more people show up to the stream, I'll do this. What would happen if we took this code? This code probably behaves similarly or very close to how the original behaved, but it doesn't produce the same binary. What would happen if we copied and pasted this code into the project and compiled it? We would see a mismatch, even though the game might work as is. All right, so we got rid of the step variable. Often comments are put in along the way, and I usually get rid of those as well because they're not relevant to what we need. So going along, One of the things that we see is here on line 14. These immediate values seem to be out of order. And that's because this particular line has been generated by the decompiler out of order. And this, again, we could tweak this around not knowing how the code base works, but from experience, the animation set and the palette are typically set in a particular order, and kind of going back, looking at both our compilation metrics as well as the assembly that's generated, 68.82%. Before I move this line, I'm going to move it up one, and now we're at 69%, and all of the differences between these two sections have been resolved. So now we're going to go down, and there's more cases like that down here. This variable related to the direction we're facing is likely going to be set down here, and the priority is going to be set after the flags, maybe even a little lower. Not quite. Oops. Well, that one's not working out like I would hope. So we'll leave that there for now. And keep moving down. Actually, this we'll see how this works out in a little bit. Another idiom that's pretty typical is that X is set before Y, so we can move this up, and that clears up a bunch as well. What's more likely is that this variable never existed in the first place, and that this was set directly. So if and that doesn't get us any closer. Oh, because we don't need that then. That's actually a little further away. We can do that change. Moving that up does get us closer. We'll save it and come back to that a little later. So GAPI is another one of these where there's a symbol that's defined to make this easier for the decompiler, which is us, but we need to access that as a struct. And finally, and sometimes these make a difference, I don't know if it's going to in this case, incrementing step is almost always done with a ++ operator. And that doesn't change anything, but it matches the other code. So backing up a little bit, changing this GAPI to struct access instead of that direct memory access gave us about 5% closer to the original. So that's case 0. So case 0 is when the weapon is created. What is the initial thing? So we're setting up sprites. We are determining what direction the player is facing to know which direction the the missile is going to be fired, and other things like that. And so then case 1, in this case, is going to be what is the animation loop for this particular weapon. So case 1, it'll keep going, incrementing the current animation frame until well, actually, in this case, it looks like it's creating some other entities, probably with smoke and other things like that, playing a sound, and then going on to the next step. So we'll look down here. There is some slight difference. One of the big things is that this particular field, as mentioned earlier on, is a 16-bit integer, but it's being compared against something that is much larger than a 16-bit integer. One thing we can do is cast that memory address as a 32-bit, and that way that comparison works. Unfortunately, that field is a little too far off when cast as 32 bits. But we can look at that again in a little bit, but that gets us to 93% similar. GAPI struct access, we'll make those changes. That gets us a little further away, but that's likely because of registers, or I guess it gets us further away because of the immediate addresses don't match anymore. Okay, so those are relatively close. There's a add here. We'll change this to a plus plus. So going back to the increment comment that I made above, setting up these, incrementing this step before, changing it to a plus plus made no difference. However, down here, changing the increment to a plus plus does make a difference and lines up that assembly perfectly. So we have a few structural things. I guess we can go back and clean those up later. But just to mention them, we have a bunch of returns within the switch, and all those returns wouldn't behave any differently than a break. I like multiple returns in functions when it makes the flow of the function simpler and reduces nesting. I don't like returns when they're superfluous. So for my own OCD, I'm going to replace these all with breaks, and I'm going to get rid of this one because it serves no purpose. That won't change the code coverage at all. It's just my own pet peeve. Finally, in this last case, we're decrementing a timer, and once that timer gets below a certain value, or when that timer gets to 0, then we're going to destroy this current entity. So this is basically a decrement. The shift is because our temp v0 variable, this comparison with the temp v0 is a 32-bit comparison, but we're doing it on a 16-bit value. The decompiler didn't figure this out, but this shift is actually unnecessary. So we can get rid of this variable by doing the decrement to the timer directly. And then using that timer And we have extra parentheses. So this will compile to the same thing. Again, it didn't change the coverage at all. Or not the coverage, the similarity between the two. But as somebody who's reading this code, if I see assignment to a variable, reassignment of that variable back to what we were originally operating on, and then some other funny business, that is much more complicated for me to read, and so I want to simplify that and get rid of it as much of that as possible. So we got rid of this variable as well during that process, and so we'll save. So now we're getting relatively close. We started at about 68%, and now we're already nearly 94%. We're having some issues in this main case 0 setup. So there's a few things in this area that we can look at. So I was wrong with the value I was setting this to before, so we'll try that real fast. So we'll take out the var a0 and set these directly, and get rid of this line. That gets us further away. Can try moving this in. No closer. Okay, and that still doesn't get us closer. So that variable likely was there. And so we can keep that variable. Let's rename it to something more human readable. We'll call it delta x. It's possible. So we're operating on a 16-bit value here. Let's try making that assigned 16-bit. That doesn't help at all. Where did our... Okay, let's try that again. It doesn't hurt, doesn't help. And we can move that out of order again, as it was when it was decompiled. Moving it out of order actually helps quite a bit, so we'll keep that. That's very unlikely to me that that was in that particular order, but the compiler likes it, so we can't argue with the compiler. So really the last thing we have now is potentially the ordering of these assignments. And once the ordering of those assignments is done, we're probably fine. I'm going to try this again, put flags above, and let's go back to some other examples. And we're going to look for places where Z priority is being set. I'm just choosing one of these at random. So the order that we typically see, palette flags Z priority. Let's go back to ours. So we have Z priority set after flags. Let's look for facing left. doing some of this in the background. Trying to find other. I'll switch this. So I'm going to look for places where facing left is being set, and then where Z priority is. We'll look for. Oops. Look for Z priority. Let's see, after 3, 4, 3. Okay, so, and we can look for this unknown C as well. So usually if facing left flags Z priority. So I'll go back and try that. So these different permutations, we can probably try a few dozen of these variations a minute. But there is a tool that can do several thousand of these a minute, and that is the decomp permuter. Try this one more time. Let's try this order. Okay, we'll go back to the original order. Save that. Now we're going to go back into the project, and we're going to paste our non-matching function in, and we'll see how. So if we build this project now, all of the built objects match what was in the original PlayStation version of the game. We're going to take our entity weapon attack, paste it in, and stop using the included assembly. We failed to build because some of these declarations don't exist yet. So I pasted in the function that we're currently working on, as well as our declarations, and we're going to build. And we fail. And we know that we failed because we're not matching in decomp.me yet. So what do? We're tweaking things in decomp.me, not getting much traction there. We can use the decomp permuter. So we're going to ask the permuter to randomize this function So we're going to import weapon 22. We're going to tell the permuter where its assembly is, and then let it run. And those ordering permutations, type permutations, and other things like that, those are going to be iterated on very quickly. We've already gone through about 500 different permutations, and the permuter has found things that result in a better score than what we've produced. So let's look at what some of those are. It outputs them as diff files. So this is recommending that we pull out the Z priority into a variable and then assign that variable. Sometimes those are valid, sometimes they're not. The other change that it's suggesting is to compare to -1, less than or equal to -1. We can try that. I don't think that that's going to be that valuable or correct, but we can try it. So here, what's interesting is places like this, there is nothing wrong with this code, but sometimes changing this, yeah, that, oh, because it's less than or equal to. Sometimes changes down here actually can make pretty large changes to code elsewhere, because the compiler needs to figure out what registers to use, and so if you give it enough hints, it may completely reorder how it's using registers, which changes how things work in other parts of the code. These particular case statements are completely independent from one another. That doesn't mean that the compiler still won't look at them as if they're a group, but I don't think that that's likely at the moment. We can look at this other one and see, so this is kind of forcing this operation to happen and be assigned a 16-bit value. And that does get us closer. Let's take that and reorder it like this. Is that even better? That's no different. Not my favorite change, because I don't think it's going to I don't think it's going to make that big of a difference. So one of the things we're doing is storing a word at offset 34, but this is happening much later. Why is this pasting this? So this got us most of the way there. Not changing any of the code, just reordering statements. It's going to produce exactly the same result. The last thing I'm going to try is inlining this. We could get rid of this. That doesn't change anything. So if we're facing left, we'll use a ternary. And let's see what happens if we inline that. Did not like that at all. Let's go back to a 32. Didn't like that. And let's try reordering. So reordering that, which is the original order the decompiler had, that matched. The ternary is a little strange, but it works, so I'm not upset by it. Let's try to put that in line. I would prefer it to be inline if I was writing the code, but I'm not. I'm just the decompiler. So this is getting the code to match almost perfectly. We have 65 bytes that are incorrect, and we're at 99.49% matching. We're going to go through and look to see what's wrong. Often we can have a perfectly decompiled function, but just have addresses wrong, these I values, so immediate values. So we have these immediates we know are the difference between the original symbol that we had and the struct access that we need. And those will come in pairs. And each one is going to be 5 bytes. So we're not, sorry, not 5 bytes, 5 units of comparison. Not concerned with that. Most of these pairs, if it's just addresses, not concerned. This is the concerning one. It's off on its own. The remaining ones I think are okay. So on line 36, this was this odd cast. And the assembly is saying load a word at offset 50, and we're loading a word at offset 56. So we need 6 bytes earlier in this entity struct. So we can look at the entity struct and figure out where we are. So we were looking at the animation current frame, this one here. So 2 earlier is the animation set. 4 earlier is the animation frame duration, and 6 earlier is the animation frame index. So we'll use that instead, and now it matches. By using this as a 32-bit instead of 16, the comparison's actually being done, and we could pull these out and see if we can match this way as well. The comparison is being done with both the index and the duration at the same time. So let's split those because that would be nicer for everybody. And so we're going to first look at the index. And compare it to index 2. And then we're going to look at the frame duration to the 14, which is actually 20 in decimal. And that gets us close, and we flip those so the frame index is 20 and the duration is 2. So the decompiler thought it was doing a 32-bit comparison of one value, when really it was doing two different comparisons of two 16-bit values that happen to be contiguous in memory. And everything else works, so we got a match. And to prove that we got the match, we'll compile that. We'll go back to our terminal. Take our function that we pasted in earlier, get rid of that one. And we're going to make, and now weapon is okay. Perfect. So we got a match. We're not quite done, but we know that we have a version of this function now that recompiles to an identical set of assembly from what was on the original Castlevania disk. So this is kind of cool, I think, being a programmer, being somebody who's interested in retro games. We don't get to see the source for most of the games. Sometimes the source leaks from dev kits and other things like that that people find along the way. So often this is going to be the closest we get to knowing how back in the early mid-90s developers were writing their games. So let's get back to some of the cleanup, which is mostly project-related macros and conventions to make our lives easier in the future and other decompilers' lives, code reviewers and things like that, easier as well. So first, the animation set, having this odd hex value that is also a negative of an unsigned, kind of odd. That's because the animation set is an unsigned 16-bit integer. What we need is something with a something that's masked basically with the highest bit set. And there's a macro to do this to make it readable. And that macro is it's based on this animation set overlay. And basically we're saying the animation set is going to be coming from the overlay memory address, not from the base game. So anim set overlay, and I think the equivalent is 10. We're going to look. Nope. The equivalent is 16? Yes. The palette, this also has macros, but this one is coming from the base game. This will do nothing to change the value, but it just helps other people know that this is a palette data type. Unknown 5A, I don't know any details there yet about what that data is. The palette down here, similar. We're incrementing that by a value, so we're not going to change anything there. Flags, these have macros. many of these are not known, so we're going to be looking for macros that may not tell us much, but are easily findable later. So this is one unknown flag. And then another. So while that doesn't give us a lot of information now, these macros are much easier to search for than random hexadecimal numbers, which may be combined with other hexadecimal numbers. So we put them in just to make future work easier. The sound effects may be defined. In this case, it's not. There is some work being done there to map all the sound effects to particular symbols. The timer is going to be 16. Sometimes, so the decompiler will also, or often, pretty much always, generate hexadecimal values for anything above a 10. In some cases that makes sense because they're flags. In other cases, as a human, I find it easier to read base 10. The same thing with this facing left or right. We can change that to 32 and negative 32. Those are easier values to understand. Draw flags. These are flags, so there's going to be macros defined for those. So we're trying to get to draw flag 80. That will be just one flag, which is draw menu. I think this is used often when there's text that appears at the bottom. I'm not sure why though. Why that would be the case for Magic Missile. It may just be a misnamed macro. Looking at this G API call, we're comparing it to null. It's not a pointer return value, it's an index. So we're just saying if it's a non-zero value, treat that as truthy. So we can get rid of the noise of that additional check. Sound effect 625. Let's see if that one's defined. No, I'm gonna actually. I haven't had Safari open for a while. Sorry about that. I'm gonna go back to the terminal and see if any of these are defined yet. They're not. And that looks like it. I don't see anything else that is going to be an issue. So we'll save here. We're going to mark this as a match because the decompiler doesn't know that our differences are acceptable. Oh, why is this not scrolling? Should be more here. I will mark that as a match later. We'll copy this code. Everything works. Now we'll get this ready for a code review. So I've gone through most of the things that I think a code reviewer would call out. One thing that the pre-merge checks we'll look for is, do we pass the standard code formatting conventions? So we can run a tool that will format things for us. We didn't change anything in symbols, so I'm actually going to get rid of that change. And I had some other changes in here that got formatted along the way. We'll review all those and make sure that those are okay. So my personal preference when doing multi-arg function calls is to line them up with along with the left bracket. That's not the coding convention for this project, so those always get changed back. Oh, that's interesting. This got automatically changed to a fixed. Cool. Okay, some number formatting, and then this is the function that we just added here. We actually need to get rid of this include ASM line. I will add this now and go back and get rid of that. Okay, so this is going to rebuild. Usually do this in parallel, so it'll go a little faster. And at the end, sometimes with weapons it fails in the middle. I need to look into why that might be happening. Got past weapons now, so we'll do that in parallel again. And there we go. Everything's okay. So now we're going to submit we'll commit the rest of these changes. I'm going to add it to an existing commit that I have of other functions that I was working on over the weekend. And then submit this to GitHub. So I have my own fork that I submit all my changes to. But then the PRs are done through the SOTN Decomp project. And so we can look at that when we go to pull requests. We'll get a notification or a banner up here that says that we just pushed a branch. We can look at the branch that's pushed, review those changes again to make sure that we like what was there. Make sure like things like flags are set to constants or macros in this case. That there's nothing really out of the ordinary. This was so here's another instance where hand ID is being used to switch, but the structure of this code is quite a bit different. And finally the function that we just worked on, and that all looks fine. So the comment is just taken from the description is taken from the commit comment. There's not really anything that's unusual in any of these functions, so I usually don't call anything out unless it's unusual. So we'll create the pull request, and now a bunch of checks will be run, which build it for various systems and make sure that it is actually a match and that the code quality is up to the standards of the project. And later on, hopefully today, somebody will come and take a look at it and merge these changes in. And tomorrow when we stream and look at another function, hopefully these will have been merged into the project. The project itself is at GitHub, Xeonimo SOTN Decomp, where you can go and look at the changes in. There's information about how to decompile there, how to get a project set up and run on your own system, and how to contribute. The leaders of this project and some of the main contributors are both thorough and rigorous in the changes that they're going to accept, super smart, but also extremely friendly and patient, which is good when you're committing to a new project and don't necessarily know what's expected of contributors. So we got that done in a little over an hour. With the remaining time, what I think I'll do is spend some time working on one of the other functions that's it's going to take several more days to work out, and that's the sprintf function. This one comes from the PS1 SDK. It mostly looks and works like a standard printf function and implementation. However, even a relatively simple and straightforward printf implementation is a reasonably complex function and goes on for quite a while, has to support a lot of different use cases. So I've kind of been chipping away at that. Still, obviously, a long way to go. The decompilation of this particular function is relatively complicated. And I may actually move to a new scratch for this one, because there's certain things, like there's these two variables which are used for mapping integers to hex values. They're misnamed, and so I've renamed them in mine, but they no longer match, and the decomp doesn't match. There's this particular variable which is used to define the default configuration for for formatting, and a few of these others that for whatever reason they don't have signatures in the context, but should. So for this particular one, I've been looking at other implementations as well to see the PS1 SDK implements kind of a POSIX Lite API, and what's interesting is that it's not exactly they didn't take like a BSD implementation, for example, and just use that. They did something different. So like right here, they're storing the difference between their code and my code is mine is looking at taking this particular byte, sign, and it's using a move instruction, which is fine. Where my compiled version is using a move versus they're storing a byte. This happens quite a bit in this particular function because they are oh, they're actually setting a flag, it looks like. So it looks like they're storing this in I don't know if this is going to work, but they are so they're treating what's normally treated as a integer as a array of bytes. So I'll take this. What are they doing? Where to set this to? Does that work? That's close. Are we any closer than before? Yes, slightly closer than before. So that's the way this function is going. This one is going to be quite the slog. There are just little bits and pieces here and there. Like I said, a printf function is complicated on its own. When you are looking at a custom function that may or may not have been pulled from another implementation of the time, probably from the late 80s, this can be relatively difficult to decompile. One of the functions that I actually came back to it after about a month was the memmove implementation, and got that sometime last week. Where did that one go? Of course, now I can't find it. You can look at GitHub. So looking at the memmove, how it was written, it's a very simple function, but looking at contemporary implementations at the time, the GNU implementation, the BSD implementation, the SRv4 implementation, this one didn't match any of those other implementations. So it was something custom that Sony wrote, and the logic itself is somewhat newer logic from the original memmoves, which potentially overwrote destinations depending on what direction the move was happening. So it doesn't have that older bug in it, but it also at the same time is not an implementation that any Unix or other open source that I could find at least system used. So if you're just tuning in, we were working on decompiling an entity weapon attack function from the Magic Missile. We were able to get back to code that compiles back to the original Symphony of the Night weapon object for that particular code. So we have a matching decompile. We submitted a PR for that, and hopefully that gets integrated sometime later today. And tomorrow we'll be back at decompiling more weapons, and I'll probably spend the afternoon looking at printf and seeing if I can get any closer with that. So if you want to tune in, I'm planning on doing this from 9 to 10:30 Mountain Standard Time this week, and depending on how that goes, I will keep doing that until we get everything decompiled. Thanks for tuning in. Please like, follow, subscribe, and watch the old videos and see if there's anything there interesting that can help you in your project. Thanks.